All right, good afternoon, everyone. Nice to see you, everyone. So today is our fourth lecture where we finally are going to look at real problems of electromagnetics. When we are done with exploring different tools of electromagnetism, we can start solving various problems. And of course, we're going to start with the simplest problem of plane wave propagation in homogeneous media. I mean, which is what can be simpler than propagation of plane waves through free space or through a dielectric. And this is the problem that we're gonna start with today. But as always, we're gonna start with recapping what we learned on the previous lecture. So last week we learned a number of tools such as the pointing theorem, which expresses the conservation of energy in electromagnetics, in optics, and with the definition of the Poynting vector. We learned the time reversal symmetry, which tells us how Maxwell's equations and fields are transformed when we flip the direction of time. We got to know the concept of reciprocity, which is also a powerful concept which allows us to loosely speaking, to connect how switching, how flipping the source of electromagnetic radiation and a detector of electromagnetic radiation preserves the detected amplitudes, the fields, the detector to source ratios. And then also we learned two small but still very useful symmetries, which is that of the scaling symmetry and the duality symmetry. And one note, when I was deriving the Poynting theorem, I made that wasn't very accurate. So there was a number of statements that I want to correct that is related to the Poynting theorem in the dispersionless transparent case. There was one thing that wasn't 100% accurate, and also the derivation of the Poynting theorem and the definition of the electromagnetic energy in the dispersive case also contained a number of not very accurate statements. So I guess maybe in a couple of lectures I'll run a short a rundum, if you will, where I'm gonna present the Poynting theorem, derivation of the Poynting theorem in transparent case and in the dispersive case. Once again, that will take us 10-15 minutes. Hopefully we're gonna have time for that. But that's gonna be somewhere in a couple, 2-3 weeks when I have time for that. But today we're gonna talk about plane waves. So what is the simplest problem of plane wave propagation that you can imagine? Tell me, in your opinion. In vacuum, of course, in free space. This is that we're going to start with today. And to describe this, we're going to consider the wave equation, that's a monochromatic wave equation, which is expressed by the Helmholtz equation in free space. Not in free space, we're gonna begin with a homogeneous isotropic medium defined by positive and real valued permittivity and permeability. And electric and magnetic fields both satisfy this Helmholtz equation. And the solutions of this equation are non-trivial solutions of this equation are plane waves. So electric and magnetic fields are expressed as certain polarization vector, which is unknown yet, times the exponential factor, the phase factor, which describes the propagation of this plane wave through the homogeneous space with positive permittivity and permeability. And k is the wave vector. All right? So if we plug this dependence of the electric and magnetic fields into the Helmholtz equation, we're going to obtain, the dispersion relation that describes the wave vector of this plane wave propagating through our homogeneous space. So this is a scalar, the dot product, the scalar product. And this is a very simple expression. From this expression, you can express the magnitude of the wave vector by taking simply the square root. If we assume that the wave vector is real valued, okay? So at this moment, let us assume that K is a certain vector in a three-dimensional space whose elements are real valued quantities. Okay, then we can take the square root from this, and we can express the magnitude of the wave vector with use of the refractive index n, which you are all familiar with, of course, in the case of a homogeneous medium, isotropic medium with real valued permittivity and permeability. This is just the square root from epsilon times u. Okay, nothing, I'm sure nothing new for you so far. Okay, but this expression tells us with what wave vector waves propagate through a medium. Okay, but this doesn't tell us anything about the polarization vectors yet, about the polarization vectors, about this curly E and curly H. We assume that they are some vectors, but we don't know them yet. So how are we gonna determine these vectors? Well, we're gonna need other Maxwell's equations, the divergence Maxwell's equations. And from these equations, we can see that K dot E and K dot H equals 0, which means that in a plane electromagnetic wave with real valued wave vector K propagating through a space with positive permittivity and permeability, the electric field and the magnetic field are both perpendicular to the wave vector. This is called a transverse wave, and the polarization of a wave is perpendicular to its wave vector. This is a transverse wave. But still, that doesn't tell us any relationship between E and H, and we're gonna learn this relationship, the mutual relationship between E and H soon. Okay, so once again, the electric and magnetic fields are perpendicular to the wave vector in a homogeneous plane wave. This is called a homogeneous plane wave, a plane wave that has a real valued K and electric and magnetic fields that are perpendicular to this K. But we also have the other two curl Maxwell's equations, and now with use of these curl Maxwell's equations, we can finally determine the relationship between E and H. And in the monochromatic case, these two equations can be written in the following form, where I made use of the fact that rotor of this equals, can someone tell me what does it equal? What is it equal to? Yeah, this is IK times the cross product E and this exponential thing. So I'm just plugging this form of the plane wave into curl Maxwell's equations and obtain this. And here we have, in principle, everything we need. We have the wave vector, which we already know, and we have E and we have H. And from these equations, we can see that once we fix any E, so let's say we have a wave propagating in this direction from left to right, or from right to left for you. And this is the wave vector. So now we can choose any electric field polarization that is perpendicular to K. We can choose this along the z-axis, along the y-axis, or linear combination, doesn't matter. And at that moment when we choose any electric fields, we automatically know the magnetic field, and vice versa. And now we can introduce another quantity, which is called the wave impedance, or medium impedance. It is denoted by Z, sometimes by eta, depending on the author. And this is the ratio of mu permittivity times permeability, times permeability of free space, divided by this factor of this product of permittivities. And using this concept, this notion of impedance, we can rewrite the relationship between electric and magnetic fields in the following way, where U is simply a unit vector which points in the direction of the wave propagation, and it is related to the wave number omega over c in the following way. So if we have a wave propagating this way, and this is the wave vector, okay, and remember that wave vector, so far the wave vectors are real, R3. And now we introduce a unit vector U, which has a unit length. So its magnitude is 1, and the unit vector which is collinear to k. And now we know the medium through which this wave is propagating, so we know the impedance, and this expression relates, it expresses the relationship between the two polarization vectors, electric and magnetic fields. So once we know the electric field, and once we know the direction of the propagation and refractive index, we immediately know the magnetic field and vice versa. From this expression, you can also relate electric field to the magnetic field. And if you look carefully at this expression, you can recognize that the three vectors that enter this expression, they form what's called a right-handed vector triplet. So if I have my, I'll draw it here. If I have my k, no, let's say my u, my unit vector here, okay, then I'm gonna have electric field like this. No, this is not working. Let me do it here. So I have u, I have the unit vector, and I have the electric field, the polarization vector. So this expression tells me that these three vectors must form a right-handed vector. That means that h must be directed in such a way that if I look from the direction of h onto these two vectors, then it means that the direction from u, according to the rules of cross product, the rotation from u to e must be done counterclockwise, right? So h, this means that h must be directed this way. So this is a right-handed vector triplet in a medium with positive permittivity and permeability. Remember, because this is important. And so if we have now, we can visualize the field distribution in a plane wave, in a homogeneous plane wave, propagating in a positive medium in this way. We have the electric magnetic fields, which in real time, if we forget about the complex amplitudes, and if you go back to real amplitudes, and remember that real amplitudes of the fields are just real parts of the complex amplitudes. They outline either a sine or a cosine shape in space, and at every point they outline, the complex vectors outline a right-handed vector triplet, and the three of them are perpendicular to each other in a homogeneous plane wave. You with me so far? Okay, so now we can use a linearly polarized plane wave, a couple of linearly polarized plane waves to construct a more complicated field distributions. For example, a circularly polarized wave. We can, for example, use an x and a y polarized plane wave propagating in the same direction along the z-axis, and we can add these two waves together with a different phase factor. For example, we can take an x polarized wave, take a y polarized wave multiplied by I, which is equivalent to a plus or minus pi over 2 phase delay, and add them together. And the result is going to be, as you will know, a circular polarized plane wave in which electric field and magnetic fields outline a circle as this wave propagates through space. And in the context of circularly polarized plane waves, there is another important concept which is called handiness of a wave. We'll talk about handiness in more details in the next term when we introduce the concept of chirality and helicity of electromagnetic field. So far, I can tell you that, so if you look in the direction of propagation, so imagine that you are here and you're looking through this wave as it propagates through space. And you'll notice that the electric field and the magnetic field can rotate in two directions, either clockwise or counterclockwise. Okay, and this doesn't change if you rotate your wave. If you travel together with your wave, if you are rotated together with this wave in space, and if you always look along the direction of propagation of this wave, you're going to see that it is rotated either, the fields rotate either clockwise or counterclockwise. And this is sort of an invariance of the wave if you don't anything to the wave itself. And this will allow us to introduce the concept of handedness, either right-handedness or left-handedness. Waves, plane waves can also be elliptically polarized, which can be achieved by a linear superposition of two arbitrary linear polarizations with different complex amplitudes. Now we can calculate the Poynting vector carried by a plane wave. From the last lecture, we know what the Poynting vector is, and we can now write the general definition of the Poynting vector for a monochromatic field, which is this. And now recall our previous relationship that related the magnetic field to the electric field of a plane wave. We can plug it here in place of H, and we can obtain the following very simple relationship. So the important consequence of this expression is that a Poynting vector in a plane homogeneous wave propagating through a positive epsilon positive mu medium is that the Poynting vector is collinear with the wave vector, with the vector u, which describes the propagation of phase, the phase velocity of a wave, because the expression in the brackets is obviously positive in this case, and we can conclude that the direction of the energy propagation is simply collinear with the velocity propagation, with the phase propagation. All right, that's not always going to be the case for plane waves. Okay, so far we have assumed that the wave vector k is a real valued vector. Remember, I told you in the beginning that we assume that k is a real value, but that doesn't have to be always the case. And in principle, k can be a complex valued vector. So let's see how it works with plane waves when we allow k to have complex vector elements. Let's say we still have a medium, a homogeneous medium with positive epsilon and positive mu. And all plane waves, of course, satisfy the same dispersion relation, this guy. Okay, because we don't have any other options. So if we write that explicitly in terms of vector elements of k, then k dot k is this guy. It's kx squared plus ky squared plus kt squared, nothing else. But in principle, some of these elements can be imaginary or complex. And in a few seconds, we're going to see that there are interesting solutions that have complex valued k and that can exist in free space. So from here, we can see that if some case, for example, kz is imaginary, we can see that the magnitude of k can exceed the k naught squared, where k naught is omega over c. So is it obvious to everyone that the magnitude of the vector, which is, and by the way, what is the magnitude of k? How do we express the magnitude of k? Let's say k squared. Is it the dot product or is it something else? It's not the dot product, it's this. It's k times k conjugated, of course. Because if you have a vector, let's say we have a vector 1, I, 0. So what is the k dot k of this vector? This is 0. But the magnitude of this vector is obviously k squared is 2. So this is why the magnitude of k can in principle exceed the free space wave number, which in some slides will be denoted as k naught. Okay, so the wave vector k, no one tells us that k has to be real. It doesn't have to be, and we are allowed to consider any combination of vector elements that satisfy the dispersion relation. And let's consider a wave vector that has two non-zero elements, the x element and the z element. And let's say that k is real and this guy, kappa z, is also real. So that the entire z elements of the wave vector becomes imaginary. We can plug this thing into the dispersion relation and we will obtain the following dispersion relation. So now notice that the plus in the previous dispersion relation, which describes homogeneous plane waves, it turns to minus. And the dispersion relation becomes completely different. Instead of this kind of spherical or elliptical-ish form, it becomes a hyperbolic. And it means that if we increase kappa z, then we can increase kx at the same time. And this dispersion equation can be satisfied with large values of kx and large values of kappa z. So this, of course, should be known to you as an evanescent wave that propagates through free space. This is an evanescent wave that propagates along the x-axis with usual phase oscillations, with some phase velocity, but along the z-axis, it describes an attenuating behavior with the rate kappa z. So kx describes how fast the phase oscillates along x, but kappa z describes how fast the field decays along the z direction. This is an evanescent wave which can exist in any medium with as long as permittivity and permeability are both positive. And like I said earlier, the magnitude of the vector may exceed the k naughts in the medium by many times because of the unusual dispersion relation that we're dealing with. And in particular, due to that property of our evanescent waves, the kx components, the kx wave vector may exceed what would be an equivalent of the wave vector in the case of homogeneous wave in the same medium. And this is something really interesting because we can introduce an effective wavelength of this wave. Let's imagine that we have our evanescent wave that propagates along x and decays exponentially along z. We at rate kappa z. So now we can introduce the wavelength, the effective wavelength along the x-axis, lambda x, which would indicate the distance between two peaks or two dips of our wave. And this wavelength, if I were to express this wavelength through the wave vector, that of course would be 2 pi over kx. And because kx can be very large due to the dispersion, thanks to our dispersion relationship with the minus, this lambda can be very small. So this means that even in free space, we can have waves that have very short wavelength that go way beyond what is accessible, what is possible with usual propagating homogeneous waves. And this is the central point of the entire near-field optics, where people utilize near-field excitations, evanescent excitations of free space, of dielectric materials, whose wavelength is much shorter than wavelength of propagating waves in the same material. And waves with such short wavelength allow people to see tiny details of the structures and information about small details of the structure that couldn't be inferred using ordinary propagating waves, whose wavelength is limited by the wave number in free space. Yeah. So the wavelength can be much shorter. The polarization of such evanescent waves is a bit more complicated than polarization of ordinary propagating homogeneous waves. Generally, we can have two classes of evanescent waves if we are concerned with their polarization. We can have transverse magnetic, TM, or transverse electric, TE waves. The transverse magnetic waves are by definition evanescent waves whose magnetic field is really perpendicular to this wave vector, to kx. Not to the evanescent decomponent, but to kx, which describes the phase oscillations. So if in our example the wave is propagating along x, it is attenuating along z, and then the magnetic field will be along the y-axis, and electric field, remember, as soon as we know the wave vector and as soon as we know the magnetic field, from Maxwell equations we can calculate the electric field without any questions. And we can obtain the electric field for this wave. And this is quite interesting. We see that the electric field has not only the z component, but also the x component, which is a longitudinal component. So this component is now collinear with the wave vector, with the phase velocity of the wave. So the evanescent wave propagates along x, and there is an electric field component which is parallel to that component of the wave vector. This is something unusual that cannot be seen in ordinary homogeneous waves. And this is a sketch that illustrates how the electric and magnetic fields are distributed spatially. So if you were to consider, again, our example of evanescent wave, whose wave vector lies in the xz plane, and if you were to make an instantaneous snapshot of the electric and magnetic fields, you would see something like this. The magnetic field is still perpendicular to everything, and it is directed along the y-axis, but the electric field outlines a more interesting shape. It has the dominant z component, but it also has an x component. And in time, as it propagates through space, it outlines an ellipse that rotates back and forth. And without that x component, it would have been just a vertical electric field directed along z. But because of the evanescent character of the wave, electric field acquires this longitudinal projection, longitudinal component, which becomes very important when we start dealing with the spin of light, spin orbital momentum, and effects that are related to interaction between spin of light and the near field optics. But we're gonna look at those effects in the next term. For now, just remember that evanescent waves become more tricky than their homogeneous companions. And we can do, of course, the same for T polarization by analogy. In T polarization, it is the electric field that now looks along the y-axis, and magnetic field has longitudinal components collinear with the phase propagation direction. Right, so the electric field polarization of the of ATM evanescent wave outlines an ellipse, whereas magnetic field is strictly perpendicular. But even with this tricky, unusual polarization, in some sense, the electric and magnetic fields are still orthogonal to the wave vector. They are orthogonal in the generalized sense. If we use these expressions, if we take the entire wave vector k, which includes both the phase velocity part and the attenuating part along z, remember this is our wave vector that satisfies the dispersion relation. And if we take the full electric field polarization, and if we use the dot product, we're going to see that these two vectors, their dot product is 0, which means their orthogonality in the complex sense. And these equations are just simple consequences of the Maxwell's equations, of the first two Maxwell's equations that express the divergence law. So in this generic sense, the evanescent waves are still orthogonal. But bear in mind, they are not orthogonal in the sense that electric field and magnetic fields are perpendicular to the phase velocity. Okay, so far we assumed that permittivity and permeability are both positive. We learned that waves in such media come at least in two forms. They can be either homogeneous waves that propagate with real valued wave vector without any attenuation, and they are the same everywhere in space. And there are evanescent waves that have complex valued wave vector that propagate along one direction, but also attenuate exponentially along the other direction. But what happens if some of the material parameters, for example, permittivity, becomes zero? Let's say permeability is positive for just unity, and permittivity suddenly becomes zero. What happens? Well, one obvious consequence is that the refractive index becomes zero, right? And that means that the wave vector is zero, and that means that the electric field and magnetic fields are just the same everywhere. They are not changing. There is no phase velocity, right? So this phase factor, this guy here, is just 1 in the entire space. Is it the only possibility? Is it the only solution that we can have in epsilon equals 0? What else can we have? What do you think? What are other possibilities?
K is a complex number, so
yeah, that's a good possibility. Let's see how it works. So we can again have ax squared minus kappa t squared equals, this time it equals 0. So in principle, yeah, we can indeed have an evanescent wave in epsilon equals 0. That's true. But I'm going to show you another possibility that also can realize even without involving this trick with evanescent waves. Let's work with Maxwell's equations in epsilon near 0. Epsilon equals 0, exactly 0. So because permittivity is 0, then the divergence equation for D is satisfied automatically because D is everywhere, is 0 everywhere in space. So we don't have to worry about that. But then the wave equation transforms to this because we don't have the epsilon part, so it's curl of E equals 0. That's just something to keep in mind. Let's now use the following answers for our solution. We're going to look for a solution in the same plane wave-like form. We're going to substitute the electric field with some polarization vector multiplied by the phase factor E to the IKR. So Maxwell's equations then turn to this. This is just, you can think of this as spatial Fourier transform of the Maxwell equation. We have already done one Fourier transform to Maxwell's equations, the time Fourier transform, where we got rid of all time dependencies in the Maxwell's equations. But now when we look for solutions in the plane wave-like form, we can make the second Fourier transform, which transforms from the coordinate r to the wave vector k to the reciprocal space. And this is the form that Maxwell's equations take when we make this transformation into the reciprocal space. And okay, so this equation is satisfied. So we need to take care of these three. And I'm going to show you that there is another kind of wave that satisfies this equation in the case of epsilon equals 0. Now this is a longitudinal wave. Remember that previously we were dealing with transverse waves when electric field and magnetic field were perpendicular to the wave vector in terms of the dot product. But now the divergence equation is already satisfied, so we don't have to worry about the transversality of the field, because the transversality of the field, the fact that k times E and k times H must be 0, they originated from the divergence equation. But now it is already satisfied, so we can consider a wave in which electric field is parallel to the wave vector k. And if I assume this, this field is curl free. So rotor curl of H, this is K times E, and now E is parallel to K, so this curl is obviously 0. So these Maxwell's equations also get satisfied. And we also find that the magnetic field must also be 0 everywhere, because magnetic field is just curl free, but that's 0. So this is a kind of wave that we end up with. This is a longitudinal wave where electric field is parallel to K, and if we were to visualize how this electric field in such a longitudinal wave oscillates with in space, we could visualize it by using these density lines. So the density of these lines corresponds to the magnitude of electric field locally. And this is something you would often see in acoustic waves or in elastic waves, where the waves are essentially are often scalar waves, and the quantity that behaves as a plane wave is, for example, the density of the material, the density of the gas that supports propagation of sound waves. And this is a longitudinal wave. Magnetic field is 0, the electric field is parallel to the wave vector, and it propagates with a real valued kx, and the value of kx can be any k, any wave vector, any real valued wave vector satisfies our equations. The only requirement is that epsilon must equal 0. So tell me in what media we can find epsilon close or equal to 0. Which media do you remember that can have permittivity close to 0? Some resonance, for example, a Lorentz resonance. Then there's going to be a frequency where permittivity crosses 0. Well, a real part of permittivity. Or a metal. Then at the plasma frequency, you're going to have epsilon equals 0. Well, there's going to be also a small imaginary part, but as long as the permittivity is very, very close to 0, then you're going to have some solution that is very, very similar to a longitudinal wave. And often, in the case of metals, these waves are called Langmuir waves or plasma waves because they correspond to bulk oscillations of the electron gas inside your medium. And these waves, they occur at the plasma frequency when permittivity goes to 0. And these plasma waves describe oscillations of the electron density of a non-interacting electron liquid or electron gas. Okay, so we have covered the cases of positive epsilon mu, of 0 epsilon. So what happens when epsilon becomes negative? Well, I think you are quite familiar with this case. Now our dispersion equation says that the wave vector must be imaginary because k squared, kx squared equals epsilon squared, which is less than 0. If we don't consider this trick with evanescence, with complex valued wave vector, and then kx must be purely imaginary, which corresponds to pure exponential decay of the fields in space. So there is no energy propagation, and you can easily verify it by calculating the Poynting vector, which in this case will be exactly 0. So the electric and magnetic fields are exactly plus minus pi over 2 out of phase with each other, and the time average value of the Poynting vector is 0. So when a plane wave hits a medium with negative permittivity, it does not transfer energy it cannot transfer energy to the other side. That's only true for a single wave. This is not true for a superposition of waves. So far we're dealing with a single wave. A single wave propagating through a medium with negative permittivity. But let's say we have a thin film, a thin metallic film with negative permittivity. and you illuminate it at normal incidence with some light, and you have these waves with the imaginary complex, with imaginary wave vector inside. And of course, you're going to have some transmission on the other side of the field. So how is it possible that that's a wave that does not transfer any energy? The Poynting vector is just zero. You can believe that's expression. You can take it as granted. How is it possible that waves, each of which does not carry any energy on its own, how is it possible that there is certain light transmission on the other side of the field? No, it is light, but it is the interference. The Poynting vector, it's not a linear function of the field. This is quadratic function. And when you have two waves, and in the case of a thin film, you're going to have two waves. You have a backward, forward propagating and backward propagating wave. They will be, of course, absolutely, these waves will be attenuating exponentially. They're going to have purely imaginary wave vectors. There's going to be interference of these two waves. And when you calculate the Poynting vector of the whole combination of two waves, you'll have non-zero Poynting vector that allows you to have some non-zero transmission to the other sides of the metallic field. So one is to be careful. This property only holds for a single plane wave. A single plane wave propagating in a medium with negative permittivity. Two waves, three waves, some superposition of plane waves, this doesn't hold any longer. There might be some energy transfer inside the system. And this is true for any media, for positive medium, for negative index medium, for negative permittivity, negative permeability, and so on and so forth. When you're dealing with superposition of waves, the quadratic quantities such as Poynting vector, energy density, dissipation density. Remember that if we have a piece of material with permittivity that has an imaginary part, then there is a dissipation energy rate associated with this piece of material, which is proportional to omega epsilon double prime E squared. Again, this is a nonlinear function of the field, and all conclusions that we made for energy transport in plane waves cannot really be applied to the case when you have a superposition of waves, because such functions are generally nonlinear, and you need to calculate the entire function before drawing any conclusion. Okay, so that was a short detour about linear and nonlinear observables in electromagnetics and how these observables are affected when we have a superposition of different fields. Back to negative permittivity medium. So the microscopic mechanism why there is no energy transfer and why there is basically no energy propagation inside negative permittivity medium is because the electromagnetic field, when it is imposed on a surface of a negative permittivity medium, it is screened by the electron gas, because there are tiny electrons bouncing back and forth in your medium, and electrons of this medium respond in such a way that they suppress propagation. They don't want electric field inside, because this is a conductor, right? And they are moving in such a direction, they move in such a way that the electromagnetic field, its propagation inside the medium, is simply screened by the electron density in the negative permittivity medium, and this is why there is no energy propagation. Okay, so now let's explore the more exotic case when both the permittivity and the permeability turn negative at the same time. And of course, we're gonna start with the same dispersion relation because it remains valid in this case, and we have to go back to this dispersion relation. So now K dot K is again positive because both epsilon and mu are positive. And this equation again admits solutions, wave vectors, the positive real valued wave vectors that describe propagating homogeneous waves. with transverse electric and magnetic fields. This is quite interesting. So the screening of the electric and magnetic field that I described previously, that works in the case of negative epsilon medium, doesn't work any longer for some reason, and the medium that has both negative epsilon and negative mu allows penetrating, propagating, allows the electric and magnetic fields to penetrate through the medium. And a medium that has such a unique property is often referred to as a double negative material or negative index medium. We're going to see later why it is called double negative index medium. So now let's explore the properties of the waves, of plane waves inside such a material. And to understand how waves propagate in double negative media, we need to accurately examine the refractive index and what actually is the refractive index in double negative medium. So we're going to use the relationship between the electric and magnetic fields in a plane wave that, of course, remains valid. Here we assume we have fixed some wave vector and some electric field polarization E. And now with use of these quantities, we can determine the magnetic field polarization of the plane wave H. And notice that mu in the denominator of this expression is now negative. And the three vectors in the set E, H, and K now form not a right-handed but a left-handed vector triplet, in contrast to positive epsilon mu medium. Simply because the sign of mu is negative and k is a real valued vector. So it is the fact that epsilon and mu are positive negative at the same time leads to this left-handed triplet. You could ask, wait a second, what if mu was negative but epsilon was positive? So mu is negative, then these two guys are, well, some vectors. And this vector triplet should also be a left-handed triplet because mu is negative. But this is not the case because k then would be imaginary or complex, and we couldn't talk about a right-handed or left-handed triplet. But because both epsilon and mu, it is epsilon and mu that are negative, the k becomes real valued, and negative mu here makes it such that these three vectors, this, and this, form a left-handed vector triplet. And now a very interesting property appears if we calculate the Poynting vector of this wave. Using the same formula, real part E times H conjugated, we plug in the H from the above expression here, and we see a very interesting result. It turns out that the energy propagation and the phase propagation are anti-parallel in such a wave that propagates in a plane wave that propagates across a double negative medium. Interesting, right? So if we were to visualize the relationship between all these four vectors now, electric field, magnetic field, K, and S, the Poynting vector, we would obtain the following picture in which electric, magnetic field, and K, they form left-handed vector triplet, and the Poynting vector is anti-parallel with the wave vector. Okay, bear this in mind, because now we're gonna using this knowledge, we're gonna define the refractive index of a double negative material, and to do that properly, we need to remember that a refractive index, the way we introduced it for positive index material, was a square root from epsilon times mu. And the square root is actually, if you look at the square root in the context of complex analysis, you realize that a square root is a two-sheet function. It has the plus Riemann sheet and the minus Riemann sheet, and you can choose whichever sheet you want, whichever you like. And For positive index materials, it was somehow obvious to us that we should choose the positive Riemann sheet of the square root function that gives us positive refractive index, and everything makes sense. What do we do in the case of a double negative medium, double negative material? Yeah. Which Riemann sheets of the square root we should choose? So it depends on how we want to define the energy propagation, how we want to relate the energy propagation to the refractive index. And usually people do the following. Usually people associate this unit vector u, which is associated, so this is our k, and we want to choose a vector u which is associated with the energy propagation. So the Poynting vector should be proportional to u. And we want to define the wave vector k as refractive index times omega over c times this u. This is exactly how we defined it earlier for homogeneous waves in positive index media. Remember, it was n, it was omega over c, and it was u that was denoting the plane wave propagation. And the difference that we are making now is that we want to associate this u not with the phase velocity, but with the energy velocity of the wave, with the direction in which the energy is propagating. And this tells us, now we know that the phase velocity and the energy velocity, the energy propagation of the wave in a double negative medium are anti-parallel. It means that n should be negative. So we should define n as minus square root from epsilon and mu, which you should use whenever you have a medium with real valued but negative epsilon and mu. This becomes a bit more complicated when you have lossy media with epsilon, when epsilon equals epsilon prime plus pi epsilon double prime, and the same for mu. Mu equals mu prime plus pi mu prime prime. Now the question is, what is the refractive index? Is it minus square root epsilon mu? Is it plus square root of the same thing? And this is quite a tricky question. I'm not gonna explore this today in details. There are papers written about that, but essentially the recipe to correctly define refractive index is to associate this thing u with the direction of the energy propagation, and then you get the refractive index according to how the wave vector and the Poynting vector of a wave are aligned or anti-aligned in a plane wave propagating across a medium with such constitutive parameters. And this is the reason why such materials are referred to as negative index materials, because the index of refraction in such a medium is negative. And this leads to a number of very, very interesting exotic effects that were highlighted back in 1960-something, 61 or 63 by Veselago. And then it was forgotten for many, many years, for decades. But then the interest to such media, to this class of exotic media, was revived by John Pendry in late 90s. And this was in many ways one of the major reasons for development of nanophotonics and near-field optics. The revival of interest in negative index media in late 90s was one of the major drivers of developments in nanophotonics in general. And then maybe a decade or something later, people lose interest to negative index media. It became clear that realization of stable negative index media in an optical range is quite challenging, and it doesn't allow you to realize the exotic effects that people originally hoped to. But nonetheless, all this led to the advances of nanophotonics in general that we're dealing with today and still exploring. So a small detour and a couple of words on how we engineer, how we realize negative index media. Optical negative index media do not occur in nature. Materials that we have in nature can have either positive permittivity, permeability, and positive refractive index. They can be, of course, lossy. They are usually lossy. Sometimes they can be hyperbolic. That does occur sometimes in the optical range and near infrared range. I'm going to talk later what hyperbolic means. And to the best of my knowledge, negative index materials with isotropic negative epsilon mu do not occur in any wavelength region, at least down to microwaves. And so if we want to have a negative index material in the visible range, we need to engineer it. And there are many ways to engineer it, but generally we need to utilize some resonance structures that induce electric resonance and magnetic resonance at the same time. And remember, if we have a resonance, then permittivity of the material can be described by a Lorentz model. And if the oscillator strength is large enough, then permittivity is going to outline something like this. It's going to be positive at energies below the resonance, then it's going to make a sharp dip, and it's going to be negative for a while in the range called the Raststrahlen band, where permittivity takes negative values. And this is achievable well in many media, in absorbers, in organic molecules, in quantum dots, in semiconductors, in a wide range of materials. But we also need the permeability to be negative at the same time. So somehow we need to engineer a material in which permeability also has a resonance at a very close value, and also dips to the negative values. Okay, so this is epsilon, and this is my mu. And when both quantities epsilon and mu become negative, here in this range we can talk about negative index material. But unfortunately, as you remember, any resonance is associated with losses and with dissipation. So all these media, they become lossy, and we have the problem with complex valued refractive index. And as the research has shown, all the exotic effects, such as negative refraction, which I showed you on the last slide, they become hugely suppressed when we have even a tiny fraction of dissipation in a negative index material. But nonetheless, there are certain ways to engineer negative index materials using nanostructures that possess electric and magnetic resonances at the same time, and usually there are some periodic structures incorporating nanoresonators, some mesh structures, some blocks, some U-shaped resonances, and so on and so forth. Okay, that's pretty much it that I wanted to tell you about propagation in isotropic media. Remember, every media that we considered so far was isotropic. It was electric, magnetic, positive epsilon, negative epsilon, but it was always isotropic. So what happens when the medium is anisotropic? How do you describe plane wave propagation across an isotropic medium? Well, we're going to have to start with Maxwell's equations again and slowly work our way to obtaining a dispersion relation. We have the Helmholtz equation, but now we can't replace this guy with Laplacian, right? Because it doesn't work in an anisotropic medium, so we have to be more careful. Again, we go to our plane wave ansatz and we substitute electric field, spatially dependent electric field, with a plane wave. That is a polarization vector, unknown polarization vector, times the usual phase factor, which we're going to determine in the following. And we arrive at this thing, which is double cross product of k plus the usual omega squared over c squared times e, where epsilon is now a tensor. This is a rank 2. This is a 3x3 matrix, which describes the dielectric properties of our medium. It can be diagonal, it can be non-diagonal, it can be real valued, it can be non-real valued, it can be pretty much anything. For the most part, we're gonna be looking at materials that are reciprocal. Like I said on our first lecture, we're gonna limit to reciprocal systems, which means that this tensor is at least symmetric. But it can have any other properties. It can be diagonal, non-diagonal, etc. So now we need to deal with this part. We need to expand this double cross product. But luckily, there is a very simple rule in the vector calculus that allows us to expand this thing. Remember that, well, this is actually quite straightforward. This is the rule how we can expand the double cross product. So it becomes a sum or a difference of k times the dot product of k and z minus the scalar product k times a, which is now scalar, multiplied by the electric field. And a shorthand way to notate this guy is also via the tensor product. You can verify it yourself that this combination of vectors is the same as calculating the tensor product of k by k and multiplying it with electric field. Now we can plug this back here and we will end up with this, where the capital K notates this tensor product. Then we have the dot product and we have the permittivity. And this is the central equation that allows us to determine the dispersion of plane waves in any anisotropic medium. So this is quite similar to an eigenproblem for a linear operator. This is our linear operator, and this is our eigenvector that we want to determine. Actually, not eigenproblem, but the core, the kernel problem, where we want to find all vectors that are kernels of this linear operator. Well, how are we going to do this? We need to equate the determinant of this matrix, because remember, this is just a 3 by 3 matrix. So we need to equate the determinant of this matrix to 0. And this will tell us all the wave vectors, the solutions of these wave vectors, the solution of this equation are all wave vectors that satisfy the original dispersion equation, and it is known as the Fresnel equation. And correspondingly, the eigenvectors of these operator will describe the polarization, the electric polarization of propagating waves. And there's one very important concept that we can introduce here, and this is the concept of isofrequency. So for any frequency omega, for any given real valued frequency omega, the set of all wave vectors that satisfy this equation is called the isofrequency. And isofrequency usually is a quartic surface in the K-space, which means it is a solution to an equation of the fourth order in the K-space. For example, that can be a pair of spheres and ellipsoid plus a sphere or something more complicated. And in the next slide, we're going to look at different examples of isofrequencies for various permittivity tensors, for common permittivity tensors. So before we switch to discussion of isofrequencies, there is another very important concept that one can introduce here, and this is the concept of group velocity in anisotropic media. You should remember from general electromagnetics that when we have a signal, a wave propagating in one dimension, propagating through a dispersive medium, there is a group velocity that describes at what velocity the signal, the pulse, the wave packet propagates through the dispersive medium. And this group velocity is simply the derivative of omega over k. And this group velocity tells you this is x, this is our scalar function. If you have a wave packet with certain width, And if you have a system with dispersive omega as a function of k, it tells you at what rate this thing, this wave packet as a whole, propagates in one dimension through the system. It is not the phase velocity, which is simply omega over k, but instead it is d omega over dk. You should be all familiar with this concept. So it turns out that we can generalize this concept to anisotropic media, to many dimensions, and define the group velocity, the vector group velocity, according to this expression. And this will tell us at what velocity energy is propagating in an anisotropic medium, where this derivative means that we take our isosurface, isofrequency, and we calculate the derivative at that point of the isofrequency. And this is just a normal. So if so let's say that we fixed a certain frequency in our isofrequency equation, in the Fresnel equation, and then the normal to the resulting isofrequency contour will point in the direction of the group velocity. So the group velocity is just pointing in the direction of the normal of the isofrequency. This is important to remember. And correspondingly, the energy flow, which is the Poynting vector, is parallel to the group velocity. So having the isofrequency of a certain medium, you can instantly understand in what direction the energy will be flowing in the system. And now let us look at certain examples of isofrequencies at common materials. So if we have an isotropic dielectric with a diagonal isotropic permittivity tensor, then the isofrequency surface will be simply a sphere in the K-space, nothing interesting. This is a sphere of radius refractive index multiplied by omega over c squared. So this is a sphere which tells you that the propagation is identical in all directions. Now let's go to more interesting examples. Let's consider a uniaxial dielectric with the matrix elements epsilon ordinary, epsilon extraordinary. So if we write explicitly the Fresnel equation for the system, we're gonna have the following two factors which describe our quartic surface. So setting either of these factors to 0 gives you a certain set of solutions. And the first equation, the first sub-equation is really simple. This is just a sphere, just like in the case of an isotropic dielectric, and this sphere describes the set of ordinary rays. These are so-called ordinary waves, which propagate with the same wave vector in any direction of the anisotropic uniaxial medium. But then there is a second sub-equation, which is more interesting because here we have different epsilons in the denominator of these fractions. And the solution to this sub-equation is more interesting. All the solutions to this sub-equation at any frequency, they yield the set of extraordinary rays, which are transverse magnetic polarized plane waves of the uniaxial crystal. And as you can see from this equation, it describes a spheroid which is elongated along the extraordinary direction of the medium, which is also called the optical axis of the uniaxial crystal. And we combine these two surfaces together, and we get the entire isofrequency of our uniaxial material. And for example, by looking at these two isofrequencies, we can instantly recognize the familiar to you effect of birefringence when a wave, a plane wave incident on the surface of a uniaxial material induces two reflected rays. one ordinary ray and one extraordinary ray that propagates with the same longitudinal wave number. But a more interesting situation arises if only one of the permittivity elements or two permittivity elements become negative. Generally, if permittivity elements, if the elements of the permittivity tensor have different signs, and we can consider two situations. So let's say our permittivity tensor be diagonal with elements epsilon perpendicular, epsilon parallel. Now consider the first case when epsilon parallel is positive, sorry, epsilon perpendicular positive, but epsilon parallel negative. So again, the form of the Fresnel equation is the same. It's still these two sub-equations, the ordinary and extraordinary rays. And in this case, the ordinary sub-equation doesn't yield anything interesting, but the set of subordinary rays now describes a very interesting isofrequency. This is a hyperboloid of type 1. This is interesting, first of all, because it is a two-sheet structure that is disconnected. Two parts of the structure are disconnected from each other. And the second reason, which is even more interesting, is that with this structure, you can have access to arbitrarily large wave vectors because of the form that Fresnel equation takes. This equation describes solutions with arbitrarily large kx, ky, and kz. And this is similar to evanescent waves. But remember that in evanescent waves, we got access to large wave vectors by paying a price, by having the wave to oscillate very, very fast with a very short wavelength in one direction, but at the same time to attenuate in the other direction. Here, the wave doesn't have to attenuate. It has real valued wave vector, which is achieved thanks to the very, very special form of the permittivity tensor. And this is again very interesting for super resolution and all sorts of effects of this type. And we can also consider the opposite situation when the perpendicular component is negative, but the parallel component is positive. So now we're gonna have another hyperboloid surface. This is a hyperboloid of type 2, which has a different shape. It is now connected surface, but as previously with this surface, you still have access to arbitrarily large kx, ky, and kz without having to pay this price of the wave being evanescent. So this is hyperbolic media for you. And just very briefly, I'm going to mention how we can engineer hyperbolic media. Again, they are very rare in nature. They do happen, as I mentioned previously, unlike negative index media. But they are quite scarce, and they can usually be found at infrared and near infrared frequencies, and not in the visible range. And if we want to engineer a hyperbolic media in the visible range, we can use something like this. We can engineer a multi-layered structure that contains alternating dielectric and metallic layers, or an array of metallic wires in a dielectric matrix. And we can describe this medium, this artificial medium, with effective medium approach, which treats the entire structure as a homogeneous medium. And if we have alternating dielectric and metallic inclusions, in this case, one can see that when there is a certain filling factor of the metallic component, one of the permittivity turns negative, and this gives you a hyperbolic dispersion. And this enables the hyperbolic behavior and hyperbolic isofrequencies in artificial structures, and enables all these exotic effects associated with hyperbolic dispersion, such as large wave vectors, negative refraction, and so on and so forth. And this is it for today. So today we covered a pretty extensive area of plane waves in homogeneous media. We discussed plane waves in general and the case of homogeneous waves with the real valued wave vectors. We discussed evanescent waves. We discussed longitudinal waves that occur in epsilon equals 0 media. We discussed negative index media. We saw how propagation of plane waves is described in anisotropic media. We learned the concept of isofrequency, and we also learned the exotic class of hyperbolic media. That is all for today. Thank you for your attention, and see you next time.